we'll use large language models to first break down the task into subtasks, basically generating a plan. And then we'll ask the large language model also give them the ability to sampling-based utility functions that we know how to call that, right? So for example, we allow them to call like grasping samplers or motion plannings in order to generate those low-level action trajectories. And then basically you can think about this sampling-based utility function really introduce the randomness for exploration in the low-level manipulation strategies. And on the other hand, this LLM really help us to break down the task so that we can narrow down the search space, so that makes the exploration much more efficient. So this two combination allows the system to quickly figure out a solution for a particular task. And also a very important part of using LLM is that we also use the language model to generate reward functions to help us verify whether each of the subtasks is successful or not. Right? So here we explicitly make use of the state information in the simulator in order to help us write this reward function. So this verified stage is actually very useful because it's not only help us to increase the data collection success rate, because the system can actually detect the failure and also correct it before moving on to the next step. But also, more importantly, it actually also helps us to collect some kind of error correction behaviors, right? So for example, if it fails, it also learn how to correct its own action. And those behaviors is actually stored in the data set, and it's very important for learning the downstream policy or improve its robustness in the end. So in the end of the process, what we're gonna get is a large multitask robot data set with very dense language label. And then on the second part, we're trying to, but however, just to mention that this data set actually is generated relying on simulation state, right? So in the end, we want a policy that's able to kind of directly infer action without simulation state. So that's why we have the second stage, which is trying to distill down those robot experience into a lightweight visual motor policy that can be deployed on the robot. So on this step, we have simple extensions on top of diffusion policy to consider multitask scenarios with language conditions, right? So now the policy is able to take in language as inputs, therefore it can infer different actions for different tasks. So this step is also like this distillation step is also very important when you compare to other LLM-based robotic system, because it's able to address some of those common limitations. So first is that it allows system to directly infer action from raw sensory input without relying on other external object detectors or state estimator. And the second is that it also allows the system to continuously improve its performance without the need of fine-tuning LLM itself, which is oftentimes a lot more expensive. So in the end, we test our system or algorithm or the framework on a large variety of tasks. Actually, all of them requires 6 closed-loop behaviors, and then a lot of them requires non-trivial common sense reasoning, which is enabled by the large language models. So quantitatively, you also observe that the algorithm is able to improve the performance, especially compared to those standard LLM-based policies, right? So the distillation step, and in particular, distillation with this verify and retry scheme really helps to boost that performance, because now the policy is able to inherit those robust retry behaviors in the end policy. So to summarize, I think today we talked about the importance of policy representation, just so that you're aware that instead when we talk about representation, instead of just talking about representation for the input and output action and observation, it's also important to think about representation for the policy itself. And then we give you one example of diffusion policy that is basically representing the policy as a iterative denoising process that is actually a very expressive way to represent the policy, and allows you to capture discontinuous, peaky, and multimodal distributions. And then I also talked about extension to address some potential issues of diffusion policy. That's basically we can scale up the data collection instead of doing tally operation. Maybe we can make use of large language models and simulation state to help us collect more robot data for different tasks. And we can also easily extend the single task policy to multitask by considering language conditions. And I think that's the end of my talk. Any questions?
Questions? have a question about the second idea, left idea to scaling up and scale down. When I found like that you have to get the scaling up, get much data, I just get a filter to avoid all the failure case. But in many cases, the robotic test failure case is very important to learn something that's negative. I'm wondering like whether there are some like idea or future work to incorporate this negative data to further improve the policy or improve other perspectives.
Yeah, I think that's absolutely right. I think the negative data is very useful. And also what we found is that the negative data is maybe potentially more helpful for generalization across different tasks, because how not to do a task or is actually more generalizable, because probably because of failure of graphs or like those kind of general common failures. I think what we did is very naive and like maybe the simplest method, just filter out all the failure examples and only keep the successful ones. But I think there's a lot of work can be done just by thinking about different ways to incorporate failure examples as well. I have a few different ideas, and I really hope that if you're interested, I can talk and then we can like continue this project. Yes, yeah.
One more question. Thanks for the great talk. I'm impressed by the great performance of the agent pricing. But is there any downside of it?
Yeah. So downside, apart from what I list out today, I think another downside that we cannot ignore is that the inference speed is very slow, right? So because it's no longer just a feedforward network, it requires iterative denoising process. So by definition, it's slower than just feedforward network. We tried a lot, actually tried a lot of different hacks to make it run relatively not too slow, but it's still like around only 2 Hz. But if you need your policy, for example, if you're running a local motion policy that really require very high rate feedback, then maybe that is not the best solution yet. Yeah.
I guess it will improve over time.
I am not working on it, but I really feel like the field, because diffusion model works so well in other fields, someone will work on it. Yeah.
So one more question.
I mean, I have the same question about like the samples and the
I have a question.
Mm-hmm.
So we saw in some of the talks today, they're talking about object-centric representation.
Mm-hmm.
So how do you feel that can be plugged into diffusion models?
Yeah, so I think it's, if we just think about how to plug it in, I think it's very pretty, like there are straightforward ways, right? So right now, our observation is just pixels. You can replace it with whatever representation that you are learning or training. It can be object-centric, can be 3D, can be NeRF. I think that is an easy way to plug in and play. But I think the deeper question is whether once you do that, is that better, right? So I think that the general question is, the general answer is that if you use object-centric representation, it's probably more sample efficient because it has the right inductive bias in your representation. But that also maybe makes this whole system a little bit harder to train, and you need to kind of optimize each of the modules by itself. So as a result, may not give you the ideal performance boost in the end. So I don't know. Until I try it, I don't know. Yeah.
Thanks, speaker.
Great.